Today we're going to be talking about the message of starlight, which is lecture 11. We receive messages of starlight by observing a star's brightness and spectrum. We are connected to stars by their light, by observing their position, their motion, their distance using Newton's laws, and their brightness and spectrum. As we've learned previously, and as you should have learned in physics, light acts as a wave and a particle all at once. In this case, we're going to be focusing on light as a wave. As a wave, light is called an electromagnetic wave or electromagnetic radiation, and the speed of light through empty space is pretty constant at about 300,000 kilometers per second. This is what we know as the speed of light. The wavelength has a spacing from one crest to the next crest, which creates the spectrum. So wavelength has to do with the distance between our two crests, and this leads to our spectrum. Light speed is the speed of propagation, the speed of light through empty space. This is very constant. You need to remember that it is a constant. All right, so as waves, sources of light can interfere with each other, just like in the ocean. Two waves can collide and either enforce each other or cancel each other out. There is actually a lab in physics where you create waves with sound, and you can cause two waves to collide and watch as the string that you're putting these waves through goes completely still because the waves are colliding and causing each other to cancel out. If they collide and make themselves bigger, you will get a bigger wave. Wavelength determines which part of the spectra light is. If we were to remember the spectrum at this point, the wider the wavelength, the slower or less energy it has. So remember, radio waves are very slow versus shorter wavelength, whereas let's say gamma radiation is super duper fast. So it kind of does this. There is not much space at all between the two crests, meaning it's very energetic, it's got very short wavelengths. We still can't see it, but it is towards the blue side of the spectrum, whereas our radio waves are towards the more red side of the spectrum. Light wave energy behaves differently energy-wise from beach waves because energy doesn't vary due to EM wave intensity. Instead, light energy is quantized. It comes in little discrete packets. Okay, so, for example, red light creates particles of 3 times 10 to the negative 19th joules. We cannot make it half of that or 1.7 times this amount, just whole multiples. And this is where it makes sense to call light a particle. Light waves are a continuous emission from their origins. They don't stop and go. It is something that continuously comes out. Our sun is continuously making light emissions. This is due to pulsations in electromagnetic fields, and thermal motion of atoms determines the energy or wavelength, which leads to its spectrum or frequency. And so this is where Wien's law comes in. The hotter the object, the shorter the wavelength, and the bluer the radiation emitted. And so hotter means we measure these pulsations through a temperature scale. A hot object will emit light. You've all probably seen the range oven where you have the spiral in the middle, and when you turn it on, when it's really, really, really hot, it turns orange. Heat leads to light. The size of the object does not actually matter, just their heat. So a smaller star, like physically smaller star, could produce more light than a bigger star just because of how much heat it's releasing. So this leads to Stephen Boltzmann's law, which is this right here. And Boltzmann's law is the hotter the object, the more energy is emitted per unit time. Basically, the more luminous it is. A luminosity is the light output of an object. It is the high light output of an object. Generally, it's used to measure the thermal energy. In astronomy, we use the Kelvin scale because of it being based off of absolute zero. So when thermal energy doubles the temperature in Kelvin, it also doubles thermal energy, which is energy due to internal vibrations and motions of atoms within the object. When atoms move really, really fast, they heat up, which if you watched The Sorcerer's Apprentice, they explained how science and magic were the same thing, because basically all a magician did was speed up atoms until they were so hot that things caught fire. And that's how you created fire as a sorcerer, right? If you haven't watched that movie, go watch it. It's good for you. Anyway, we're looking at how hot are these objects. So we can't use Celsius or Fahrenheit because their 0 degree is not based off of absolute zero. So when temperature doubles in this scale, it does not actually mean their thermal energy is also doubling. Versus Kelvin, which, absolute zero is zero. It's cold. And if the temperature goes up, the thermal energy goes up. So earlier we said light is a wave, but it also happens to work as a particle because it has these discrete packets. Light has a property that acts like a bullet, and we call it a photon. These little bullets are constantly firing. The energy of light is concentrated in individual photons. So the shorter the wavelength, the more energetic the photons, the more they're bouncing around. This originates from emission lines and bands, and when electrons are no longer drifting freely but attached to atoms. Okay, so a photon is released in the opposed state. If you remember this from the last lecture, we have a hydrogen atom with a proton and an electron, and when they are both spinning in the same direction, they are aligned. And when you have the proton spinning one direction and the electron decides to spin the other direction, this is known as the opposed state, in which a photon is released. In practice, scientists will use whichever model that best describes or explains a particular phenomenon that they are studying. So for example, a mirror. Light reflects from a mirror, and this is easier to understand or imagine if you imagine photons striking the mirror and bouncing back off. So here's our mirror. Light essentially bounces off as these little photons rather than a wave hitting and then bouncing back off. But the focusing of light through a lens is better understood if you imagine it as a wave. Next lecture, we will talk about measuring each of these different properties. But the properties of stars themselves include the mass of the star, the distance the star is from us, a star's luminosity, its temperature in Kelvin, its composition, what's making it. Is it hydrogen, helium? Is there sodium? Is there lead, etc.? The motion or speed of the star, how fast is it rotating? How fast is it moving? In general, the rotation or revolution of the star, and the size of a star. So remember, stars also have their own orbit around the center of their galaxy. Our star and our solar system are currently revolving around our galaxy. The speed of that motion is important, just as the speed of the star's rotation is important. The position of stars for study are based on the celestial sphere. Stars can appear to move, which is the parallax or distance measure, and can actually move on the celestial sphere, which we call tangential motion. In order to observe the motion of a star, you need to find the force that moves it. So we have two different types of movement. Parallax, where it appears to move, and when it actually moves, which is tangential. So we're going to review the laws of motion and force before we go into this any further. Newton's first law of motion was inertia. A body remains stationary or moves in a straight line unless another force acts upon it. So think of playing pool. You hit the cue ball. The cue ball moves in a straight line because you pushed it with your cue stick. If we were in space, that ball would continually keep going after you hit it with your cue stick until something else hits it. So let's say it hits another ball, which may put it in a different direction, and that new ball will start moving. Law number 2, force is equal to mass times acceleration or motion, just as mass times acceleration is equal to force. And third, action, reaction. Every action has an equal and opposite reaction. Force, when we're talking about it here, is equal to gravitational force if no other force exists. Okay, so that's a side note. So let's talk about Newton's law of gravitation, force, mass, and distance. Gravitational force, or gravity, between two objects are attractive, proportional to its mass. So if they're heavier, you have stronger gravity, and it is inversely proportional to distance. The closer the object is, the greater the gravity. Remember, force of gravity is equal to g little m times big M over distance squared. Now let's apply Newton's laws. How do we actually use this? You remember, this guy made his laws when he was home during an epidemic because he couldn't go to college, right? Well, how do we use it? He made this so long ago. What could we possibly use it for now? Well, calculus is very important. But we use it for rockets and spaceships. This is how we have put manned and unmanned space flights, any kind of rocket, including the Falcon X, I think it's called, which is part of the space program that Elon Musk is working on. If the rocket never makes it up, it's because they miscalculated something and gravity has won, basically. When you have it passing through and managing to get up into the other upper atmospheres beyond the effect of gravity to the point where it can now orbit around the Earth or go further, you have done your calculations properly and you have managed to get your force to be greater, your escape velocity to be met or exceeded. This is how we've managed to start exploring the moon. This is how we've started exploring our own solar system. This is why we are able to have satellites up in space, is because of his laws. How can we measure the mass of a body using orbital motion, though, like a star or a galaxy, etc.? So step 1, you observe the orbital motion, which is RV. Step 2, you calculate its gravitational force. Step 3, you measure distance. And step 4, you calculate the mass, since the gravitational force is dependent on the mass and distance of an object. And this is how Newton's laws help us study the objects in our night sky. There is an effect of distance on light as well. We just learned about Newton's laws, but now we're going to learn the effect of distance. Distance is very important for measuring a body's mass. We notice when we look up in the sky that some stars are very dim and some stars are very bright. And you're automatically going to assume, oh, that star must have more energy, it must be bigger, it must have a higher heat output. Wrong. Distance has an effect on light. We have all seen, I'm hoping we've all been on a plane or we've been a distance from something bright, where as you get closer to it, it seems brighter. This is the effect of distance on light. Photons will have a constant speed through travel, which makes you think light should always look the same. But because of distance, they can appear dimmer, or we may not even be able to see them at all with our naked eye. This dimness is a result of light spreading out over larger and larger areas as a photon moves away from its source. And this is where we get things like apparent brightness, which we are going to learn about soon. And we will be working on actually calculating this. So apparent brightness is very dependent on distance, whereas luminosity is not dependent on distance. Image traces of the movement of 36 protons as they move from 1 astronomical unit squared to 3 astronomical units squared. The number of protons in an area decreases as distance increases in this case. By tracing the movement of 36 protons as they move from 1 AU to 3 AU, the number of photons in an area actually decreases as distance increases, meaning they go from being all clustered like this as they move to actually spreading out more. And this can be explained with 4 pi d squared. This explains why inner planets receive more heat than outer planets, and the change in amount of visible light with distance is known as an object's brightness. Brightness is the total light output divided by 4 pi distance squared. This is known as the inverse square law because light becomes dimmer with an increase in distance. So because these photons, remember, light happens as both a wave and photons. We receive heat from light. So our sun gives us heat. Where we are located in our solar system allows for us to have the proper amount of heat in order for us to survive. The closer you are to the sun, the more heat you have. The farther you are from the sun, the less heat you have. And this has to do with as light travels, these photons go from being super clustered to being more and more spread out until they're so spread out that the heat that you receive is so much less and the sun appears much dimmer. Today we're going to be talking the most about luminosity and brightness. Luminosity is measured in watts like a light bulb. It is the total amount of energy output. It's not measuring in anything related to distance. It is output. How much heat or energy is this light bulb giving off. So we have a light bulb of 25 watts. That is its luminosity. That's how much energy output it has. The intrinsic of the physical properties of the star itself is what this is based on, and it does not depend on the distance of the observer. You as the observer are not important in luminosity. It has to do with total energy output. And this depends on temperature, the size of the object, and again, it is measured in watts. Brightness, on the other hand, is measured in watts per meter squared. This is directly proportional to distance. Remember, inverse proportional. The farther you are, the dimmer it is. This is the total amount of energy received, not output, received. This is where being the observer comes into play. Depending on where you are, okay, so here's observer 1 and observer 2. And here's our star. Observer 1 will receive a lot more energy than observer 2, who will only receive some of it. So the brightness here is actually going to appear higher than the brightness here. This depends on, as seen by you, the luminosity, the distance, and it's measured in watts per meters squared. All right, so now let's compare luminosity and brightness. Over here we have a 75 watt light bulb. That is its luminosity. Its luminosity is 75 watts. That's how much output it has made. This is equivalent to 3 times brighter than a 25 watt light bulb. Mathematically, the ratio can be answered as 3 times equals 75 over 25 watts. So basically, you have a 75 watt light bulb. That's how much energy it is, energy output. But let's say you are this far away. Because your distance is so far, it will appear to be, or you will receive the energy of a 25 watt light bulb. And that's where brightness comes in. So if you are up close to a 75 watt light bulb, you will receive that 75 watts as energy output and energy received. The farther you go away, the less energy you will receive and the dimmer that 70 watt light bulb will look. Once you reach a certain distance, your light bulb will look like it is 25 watts. And this is where apparent magnitude, which we are going to know as little m, and this is where Hipparchus comes back. The Hipparchus classified all visible stars viewed with the naked eye from a magnitude 1 to 6, with 1 being brightest and 6 being dimmest. In the 1700s, Herschel realized that a magnitude 1 star is 100 times brighter than a magnitude 6 star. And so the difference in magnitude is 5, because 6 minus 1, which corresponds to differences in brightness ratio of 100 times. Brightness is then apparent magnitude or apparent visual magnitude because it depends entirely on the observer's distance. Absolute magnitude is based on luminosity, and it is known as big M. The intrinsic of physical properties of the star, not on the observer, meaning we're looking at output, not received energy. It is also known as absolute brightness or absolute magnitude. If all light bulbs or stars are the same distance from us, then and only then will the brightness of a star represent the luminosity of the star. Brightness at the same distance from us is defined on absolute magnitude. We measure distance in multiple different ways. The first one is using laser or radar. In this case, a transmitted signal leaves Earth, travels at the speed of light, which we are going to call c, and then the reflecting signal travels back at the speed of light, and arrives back at Earth t seconds later. And because distance is the inverse here, it's 2d equals speed of light times time. Next, we have triangulation, where you essentially use observation and trigonometry in order to figure out how far away a star or celestial body is. The observers in this case are distance b apart, where you get angles A and alpha and beta from this. From baseline b and the angles that you have, you are able to solve for d or distance using trigonometry, in which case d distance equals angle B, or angle beta, tangent alpha. And then we have the parallax. When an object is farther away, it will shift less when you go from eye to eye. So basically, our example here is fingers. If we were all to hold a finger out or a thumb out full arm length, focus it on something that is far enough away from you, close one eye, your thumb will appear to be in one place. Now close the other eye. Now it appears your thumb has moved. This is the parallax. When an object being farther away, that shift is less than when it is closer. So if you were to move your thumb closer to your face and do the same thing, that movement as you're opening and closing your eyes is much greater than it was when your arm was at full length. So when the object is farther away, the shift is less, and you'll have a smaller angle shift. And this shift is known as the parallax angle. The distance is inversely proportional to the parallax in this case. So d equals 1 over parsec. So if an angle is 1 inch, the distance would be 1 parsec. So 1 parsec equals what? Well, we can measure that in kilometers, miles, etc., an astronomical unit. You have a light year, and then you have the parallax second, or parsec. With miles, kilometers, we use that to measure distances on Earth. Astronomical units is the average distance from the sun to the Earth, which is 149,598,000 kilometers. A light year is the distance light travels for 1 year. 1 light year is equal to 9.46 times 10 to the 12th kilometers, or 63,240 astronomical units, or 0.3066 parsecs. Okay, and a parsec is equal to 3.26 light years, or 3.1086 times 10 to the 13th kilometers. So it's just a new measurement that we're going to use here. It is for farther distances. Okay, so back to absolute magnitude. Brightness or apparent magnitude of a star is when the star is at least 10 parsecs away. And the effective distance is inverse squared law, so 1 over d squared. So now let's use this as an example, our sun versus other stars. The apparent magnitude of our sun is minus 27. The apparent brightness or solar constant is 1,268 watts per meter squared. Other stars. A magnitude 1 star is 2.5 times to the 28th times dimmer than the sun, or about 16 times 10 to the 10th times dimmer. Distance in this case, we have 1 astronomical unit. An absolute magnitude, if we were to move the sun to minus 27 from 4.8 times 10 to the 6th parsecs to 10 parsecs, we would get absolute magnitude of 4.83, which is close to 5. Meaning our luminosity is 3.839 times 10 to the 26th watts. For other star, luminosity is in solar units because we're using the sun as a base of 1. You have an absolute magnitude of 5, your luminosity in solar units is 10,000, 0 is 100, 5 is 1, and 10 is 0.1. Alright, so we are going to do this in class. It will make much more sense when we actually get a chance to do it in class. But essentially what ends up happening is you will have a little m of, let's say, minus 5. Now you're going to move that star to 10 parsecs from Earth. If you move closer, your luminosity will actually increase, versus if you move farther from us, it will decrease because your apparent brightness is brighter than the star actually is outputting of energy. And that is our lecture for lecture 11, and I will see you guys next time.